and later would go back and test the ground grids after they was installed and inspect them during the course of installation. Or if there was an existing power plant that had a problem, or a petrochemical plant, or a textile mill, or pulp and paper mill, or even hospitals. I focus now on hospitals and data centers. We do a lot of inspections on grounding and bonding systems. My expertise is in ground fault protection, surge protection. I'm the chair of the IEEE Power Engineering Committee for surge protection. We write standards for all surge protected devices for both low voltage and high voltage. I represent Schneider Electric on a variety of UL and IEEE committees and ANSI committees related to grounding and bonding and surge protection and transformer and ground fault. We also provide technical support to Schneider Electric and our introductions to changes or code changes to the National Electrical Code, so we do submit those changes. We were very intimately involved in the Article 285 dealing with surge protection and often make numerous committee changes, recommendations for the National Electrical Code. We provide technical support for those. So we also do training. We provide training for Schneider Electric through Schneider Electric University, where we train other engineers and representatives, field service representatives, assembly plant engineers on the aspects of power distribution, grounding, bonding, ground fault protection, surge protection, and general control designs. Those are part of the services we provide through Schneider Electric University. So is that enough stuff? Okay.
What's your time now, so we know where the show is?
We're 21 minutes.
Okay. All right. The plan passed. You need to take a drink?
Yeah, let me take a drink. We're going to talk about basic principles. You want to get into that? Okay.
You ready?
Yeah.
What are the different three-phase power systems and machine transformer winding configurations of data centers?
Most data centers today utilize three-phase, four-wire power distribution systems. However, there are a few out there that employ three-phase, three-wire distribution systems, and they operate completely different. The classical three-phase, three-wire distribution system is one that was employed in this country almost predominantly until the early 1960s, mid-1960s. This was the three-phase, three-wire ungrounded delta system that goes all the way back to the utilization of Tesla's three-phase polyphase motor. During World War I, World War II, Korea, and the early parts of the space race during the early 60s, a lot of power distribution systems were three-phase, three-wire ungrounded delta systems. That started to change in the mid-1960s, beginning in the late 1950s, and took a predominant change in our power distribution systems because we started having serious energy crises. We had a space race going on, we had a Vietnam War going on, we had a consumer society, we had the Great Society. We were expanding the economy dramatically in the 1960s. Consequently, we needed to focus on energy conservation. And our power systems began to be converted from 40 volt, for example, three-phase, three-wire ungrounded delta systems to a three-phase, four-wire solidly grounded systems. We still have some of the ungrounded systems today. They make up less than 5% of all the power distribution systems in all of North America. But the three-phase, three-wire ungrounded systems are in a delta configuration historically. However, today, those same transformers are not so much three-phase, three-wire ungrounded deltas as they are three-phase, three-wire ungrounded Ys. Ungrounded systems, by their nature, have no direct electrical connections, but are capacitively coupled to the ground plane via the capacitive reactance caused by busway, conduit. Conduit and wire is a classic capacitive type of device. For example, a capacitor is nothing more than an insulator surrounded by a conductor surrounded by an insulator in contact with a conductive surface, usually the earth. So conduit and wire has a capacitive reactance. Are they completely 100% isolated from earth? No. They're capacitively coupled through a high impedance capacitive reactance. Consequently, when you have a ground fault on an ungrounded systems, you don't get a lot of high current flow. However, you get a charge and discharge of this capacitive reactance in the system that can cause some transient overvoltages that have historically can damage motors. There's the infamous case during World War II where there was a aircraft manufacturing plant on the West Coast that was shut down, where they had an arcing ground fault in a contactor, and it began damaging the transient overvoltages in the range of 6 to 8 times the phase-to-phase voltages. Actually blew out the windings of 50 or so motors. That's a classic case. Still happens today. However, today, if you ordered a 3-phase, 3-wire ungrounded system, most likely the utility company is going to provide you a 3-phase, 4-wire transformer. They're just not going to connect anything to the XO terminal. So therefore, it's operating as an ungrounded system, but it's operating as an ungrounded Y system. Consequently, the transient overvoltages during a phase to ground fault are significantly higher, instead of the 6 to 8 times the phase-to-phase voltage in a transient overvoltage condition for a 3-phase, 3-wire ungrounded delta configuration. In a Y system, the voltages can be as high as 16 times, which causes motors and things to fail very, very rapidly. Specifically with data centers, this is why we don't recommend ungrounded systems for data centers. For one, delta systems or ungrounded Y systems by their nature are inherently unstable. There is no centered reference voltage. And during a phase to ground fault, then you have some very, very high transient overvoltages that generally have a negative effect very rapidly on sensitive electronics that are inside data centers. And since data centers are predominantly filled with sensitive electronics, this is one of the reasons we don't recommend ungrounded systems. Also, if you have a surge protected device on an ungrounded system, the code actually prevents them. Article 285 has a code article concerning do not install them on ungrounded systems unless they've been specifically listed and designed for them. There are very few overcurrent protected devices, or, excuse me, clarify that, there are very few surge protected devices that can be successfully employed on ungrounded systems because of the transient overvoltages are so high during an arcing ground fault that they have a tendency to explode or flash over and become defective. Since arcing ground faults are the most common type of fault, and it even goes back when they were ungrounded systems, between 95 and 98% of all faults are phase to ground faults, where one of the phases, one of the conductors on one of the phases makes an inadvertent contact to earth, either through an arc or a gradual connection or a bolted connection. Bolted connections are very, very rare. Usually it's a broken insulation breakdown where you have some arcing and pitting between the energized conductor and earth. And in an ungrounded system, you get this charging and discharging of this capacitive reactance in the system, and you get some very huge transient swells. It just bounces all over the place. And it breaks down insulation very, very rapidly. And that's why we don't recommend them. However, they do exist. Some data centers want them because their argument is we're not employing phase to neutral loads. We're concerned about ground fault, which we'll talk about in a moment. Most people don't want grounded systems because they don't want ground fault conditions. Well, it's very hard to avoid ground fault conditions. Quite frankly, I would prefer to have a solidly grounded system or resistively grounded system in a data center than I would an ungrounded system. Because an ungrounded system, you create these huge potential swells during a ground fault condition where the transient overvoltages can damage equipment in the hundreds of millions of dollars throughout your facility very, very quickly and not be near where the original fault occurred. Now, the other thing that's required in ungrounded delta systems or ungrounded Y systems is they have to be monitored.